Hello everyone, welcome back to my channel. Today, we will explore a very exciting idea: how artificial intelligence can make fluid flow simulations sharper, clearer, and more useful. In subsurface engineering, we often simulate how fluids move underground. These fluids may be CO2 for carbon storage, hydrogen for future energy storage, hot water in geothermal reservoirs, oil and gas in reservoirs, or even groundwater in environmental systems. But there is one big problem. High-resolution simulations are expensive and slow. Coarse simulations are faster, but they can miss important details. So today, I will show how advanced deep learning can act like a resolution engine. It can take blurry, coarse simulation results and recover sharper flow patterns. The goal is not only to create beautiful images. The real goal is to support better monitoring, better prediction, and safer decisions for sustainable subsurface energy. Transition. Let's first understand the problem. Here is the main challenge. When we run a fluid flow simulation at low resolution, the result may look smooth and simple. But underground flow is not simple. It can contain sharp plume fronts, small leakage pathways, pressure gradients, and complex flow channels. In this slide, you can see 4 ideas. The ground truth is the high-resolution flow field. It contains many detailed structures. The coarse simulation is much blurrier. It gives the general shape, but it hides many important details. The deep learning enhanced field tries to recover the missing information. Finally, the error map tells us where the model still makes mistakes. This is very important because in real field applications, a small missing detail can become a big problem. For example, if we miss the leading edge of a CO2 plume, we may place monitoring wells in the wrong location. If we miss a pressure hotspot, we may underestimate geomechanical risk. So the question is, can AI help us recover these hidden details? The vision is to build an AI resolution engine for subsurface flow. The idea is simple. We start with a coarse flow field. This can come from a fast reservoir simulation, a reduced grid model, or limited field observations. Then we pass this coarse information into a physics-aware encoder. This part helps the model understand important physical features, such as pressure, saturation, plume movement, and geological structure. Next, the neural operator or deep learning core learns how flow patterns evolve in space and time. Finally, the model produces a high-resolution output. This output should show sharper plume fronts, better pressure details, and uncertainty information. The most important point is that the AI model should not only learn pixels. It should learn flow behavior. It should preserve moving fronts, recover gradients, and quantify where it is confident or uncertain. Now let us see the training workflow behind this idea. This slide explains the full workflow in a very simple way. Step 1 is to generate flow fields. These can come from reservoir simulators, laboratory experiments, or synthetic Python simulations. Step 2 is to create coarse observations. This means we intentionally reduce the resolution, like converting a high-definition image into a blurry image. Step 3 is to train a super-resolution model. We can use different deep learning models, such as UNet, C1BLSTM, Fourier neural operator, or a hybrid model. Step 4 is to evaluate the model. We should not only check image error. We should also check physical metrics, such as plume front error, structural similarity, and mass drift. Finally, step 5 is to deploy the model with uncertainty. This means we generate decision-ready maps that show not only the predicted plume, but also where the model is uncertain. When the model learns well, the error should reduce through time. This slide shows the learning process. At the beginning, the model may produce large errors. The coarse error is often spread across a wide area. This means the model does not clearly know where the plume boundary is. But as training continues, the deep learning model learns the structure of the flow. The error becomes smaller and more localized. On the right side, the error curve decreases as training progresses. This means the model is improving. In a good case, the AI-enhanced model can produce much lower error than the coarse baseline. But we must be careful. A low average error is not always enough. For subsurface decisions, we also need to know where the error happens. If the error is located near a moving front, a leakage pathway, or a pressure hotspot, it may be very important. So, for scientific research, we should report both image quality metrics and reservoir decision metrics. Next, let us look at the dynamic plume demo. Now we start the dynamic simulation demo. Here, we use a simple Python model to create a moving fluid plume. This is not meant to replace a full reservoir simulator. Instead, it is designed as an easy visual demonstration. It helps everyone understand the basic idea without needing advanced reservoir engineering background. As the animation plays, you can see the plume moving through the domain. The fluid starts from one region and gradually migrates. The shape changes with time because of advection, diffusion, and heterogeneity. This is similar to what happens underground. CO2, hydrogen, water, or heat does not stay fixed. It moves, spreads, and interacts with the geological structure. Therefore, a useful AI model must understand not only one image, but also how the flow evolves through time. Now we compare coarse input and AI-enhanced output. This slide explains super resolution using a simple visual comparison. On the left, we have the ground truth. This is the high-resolution flow field. It contains sharper boundaries and more detailed structures. Next, we have the coarse input. This is what we may get from a fast but low-resolution simulation. It captures the general plume location, but the details are missing. Then, the AI-enhanced result tries to reconstruct the sharp field from the coarse input. This is similar to scientific high-definition upscaling. But here, the goal is not only to make the picture look nice. The model should recover physically meaningful features. Finally, the error map shows where the AI prediction is still different from the ground truth. This is very important because the error map tells us where we should be careful. Now, let us see how training reduces the error. This slide shows a simplified training demo. During training, the AI model sees many examples of coarse inputs and high-resolution targets. At each epoch, the model updates its parameters and tries to reduce the difference between its prediction and the ground truth. The orange curve represents the deep learning model. The cyan curve represents the coarse baseline. When the orange curve becomes lower than the cyan curve, it means the AI model is producing better results than the original coarse simulation. This is a very important message for a global audience. AI is not magic. It improves because it learns from examples. It sees many flow patterns, compares its prediction with a true high-resolution result, and gradually learns how to recover missing details. However, we should not only train for many epochs. We need good data, good metrics, and physical checks. After prediction, we also need to know where the model can be trusted. This slide introduces uncertainty. In real subsurface applications, prediction alone is not enough. We also need to know how confident the model is. For example, if the model predicts a plume boundary, we need to ask, is this boundary reliable? Or is the model uncertain in this region? The uncertainty hotspot map helps answer this question. Brighter or more intense regions indicate where uncertainty is higher. These areas may be caused by fast-moving fronts, limited training data, strong heterogeneity, or complex flow behavior. This is very useful for monitoring. If an uncertainty hotspot appears in one region, we may choose to collect more data there, place sensors nearby, or run additional simulations. So, uncertainty is not a weakness. It is guidance. It tells us where we need more attention. Next, let us connect this idea to decision-making. For field safety, the plume front is often one of the most important targets. The plume front tells us how far the fluid has moved. In CO2 storage, it can tell us where the CO2 plume is migrating. In hydrogen storage, it can help us estimate the working gas region and possible loss. In geothermal systems, it can help us understand thermal breakthrough. In this slide, the AI-enhanced plume is compared with front tracking lines. These lines represent the estimated moving boundary of the plume. Even if the average image error is low, the front location can still be wrong. And if the front location is wrong, monitoring plans may also be wrong. That is why we need decision metrics. We should measure front distance, plume area, mass balance, pressure footprint, and risk area. Now let us see how prediction becomes action. This slide shows the practical value of the AI enhanced map. Once we have a sharper forecast, we can use it to support decisions. For example, we can identify monitoring points, risk hotspots, and regions where additional data are needed. In this slide, the map shows possible monitoring locations around the predicted plume and uncertainty regions. This is the bridge between artificial intelligence and real engineering. The AI model should not stop at prediction. It should help us answer practical questions. Where should we monitor next? Where's the risk highest? Which area needs more simulation? Which operation strategy is safer? For carbon storage, this can support leakage monitoring. For hydrogen storage, it can support safe cycling. For geothermal energy, it can support heat front tracking. Now let us look at the simple Python logic behind the demo. This slide explains the Python demo in a simple way. For each time frame, the code first generates the truth. This is the high-resolution plume. Then, the code creates a coarse version by downsampling or blurring the high-resolution field. This represents what a low-resolution simulator or limited observation might provide. Next, the enhancement model tries to recover a sharper field from the coarse input. Finally, we evaluate the result using error metrics and front metrics. The important message is that the demo is simple, but the logic is real. This is the same basic structure used in many advanced AI workflows. Generate data, create input-output pairs, train a model, evaluate performance, and visualize the result. This makes the idea easy to explain to students, researchers, and the general public. Now, let us discuss which algorithms can be used. There are many deep learning models we can use for this problem. Each model has a different strength. UNIT is very good at image-to-image learning. It can recover local boundaries and plume shapes. CONVLSDM is useful when time is important. It can learn how the plume changes from one time step to the next. Fourier Neural Operator, or FNO, is powerful for learning long-range spatial patterns and operator mappings. A hybrid model can combine image detail, time evolution, and physics constraints. The key point is that we should not only use one model and claim success. For strong research, we should compare multiple algorithms using the same dataset, the same train test split, the same evaluation metrics, and the same physics checks. That makes the study more reliable and more publishable. Now let us see how this demo can scale to real reservoir studies. This slide shows how we can move from a simple Python demo to real reservoir applications. Instead of synthetic data, we can use outputs from real simulators such as CMG, OPM, MRST, or other reservoir simulators. These outputs may include pressure, saturation, porosity, permeability, temperature, or geomechanical variables. Then, Python can process these data into a machine learning dataset. We normalize the variables, split the data into training and testing sets, augment the data if needed, and save everything into tensors. After that, we train an AI resolution model, such as UNet, FNO, or a hybrid neural operator. The final result is a set of decision maps: plume front, uncertainty, hotspot, pressure risk, or monitoring priority. This means the same simple idea can become a real research framework. Finally, let us summarize the key message. Let us close with the main message. Deep learning is useful for subsurface engineering when it helps us make better decisions. The goal is not just to generate beautiful AI images. The real goal is to recover what coarse grids hide: moving fronts, pressure patterns, and fine-scale pathways. We also need to measure what matters. That means front distance, mass drift, uncertainty, and risk area. These metrics are closer to real engineering decisions than only pixel error. Finally, we need to convert AI into field action. This means using AI-enhanced maps to guide monitoring, improve safety, screen many scenarios faster, and support risk-aware operations. So, The one sentence for the audience is this: deep learning becomes useful when it turns simulation detail into trustworthy decisions. Thank you very much for watching. Please subscribe to the channel for more videos about AI, geoscience, carbon storage, hydrogen storage, geothermal energy, and sustainable subsurface engineering.